Hello, everybody. I'm very happy to host Nir Rosenfeld class. Nir is an assistant professor of computer science at the Technion. His research lies on the intersection of machine learning and human behavior. And today, he will talk with us about strategic classification and beyond. Nir,
Hi. Okay. צריך וידאו ואודיו לזום? לזום, צריך להיות בווידאו ואודיו? או שזה עובד? לא? לא שלי. של הכיתה? אוקיי. בסדר. אוקיי. Hi everyone, I'm Nir. Nice to meet you. Some familiar faces. Nice to be back. Today I'll talk about strategic classification and the quest for the Holy Grail. An outline of what I'll have today. So I'll talk about what is the Grail as motivation, set up for the talk. Then I'll talk about strategic classification, which is a neat problem, which I hope you'd like. Then I'll talk about what we can do beyond strategic classification. And then I'll talk about what we can do beyond strategic classification. And then I'll try to summarize. Okay. I'd like to start with a worn out metaphor of machine learning, which is that machine learning is a black box. Now, what does the story tell us? It tells us that when you look at machine learning from the outside, and it's very hard to interpret what goes on the inside. That may be true, maybe not, but I think it misses half of the story, which is what happens when you look from the inside out? How does the model see the world beyond its box? So luckily, I have a 6-year-old who was very happy to crawl inside a box and take a picture. And this is what it looks like from inside a black box. Now, the reason you see anything at all is because we poked 2 holes in it, one for input and one for output. Other than that, you see nothing. And what I'm trying to convey by this metaphor is that the classic view of machine learning is this. There's a machine, gets input, produces output. This is in every textbook and every course, in every system that you go to. This means that the system is completely unaware of the context that it operates in. It can work in a bank, in a library, anywhere really. It just doesn't know where it lives. There is no context encoded into the learning algorithm or the model or the loss or any aspect of the learning problem. In our lab, we look at a particular kind of context, which is context that comes from human behavior. So these would be systems where you take learning algorithm and place them inside bigger systems that somehow humans take part in. And the main question we ask is, how should we design learning algorithms when we know they are going to be used in these sort of social contexts and social systems? Sorry. Now we have an elaborate vision. I won't go into details, but you can imagine your favorite fully integrated human machine system, whether you like it or not. But operationally, we look at these 3 there are many ways in which humans and machines can interact. You can think about interface, that's not what we do. You can think about ethics, fairness, privacy, that's also not what we do. We have this very pragmatic view of how do you connect these 2 pieces together. The simplest kind of connection is this. We call this upstream humans. So what you have is a machine whose inputs are generated by human behavior. These sort of problems are very conventional. They look like other learning problems in speech, vision, NLP, whatever. It's just that the input gets its structure from how humans behave. And what we do is we use knowledge and theory about human behavior so that we can design useful systems that know how to utilize this sort of structure. But today I want to talk about a slightly more elaborate sort of task, which we call downstream human. This is what happens when you take a machine, deploy it in the world, and then humans do something with the output or with the model itself. And what we'd like to do is learn in a way that takes into account the fact that humans are going to use it somehow. Okay, today the talk is going to be very high level. I'd be happy to get into details if you ask questions, but the things I've prepared are very, very high level. And the general broad question I'd like you to think about as we go through the talk is, how do we get from this classic perspective of no humans at all to this very nice yin-yang thing? And I'd like to start with what I believe is a very good first step towards this goal. And that is strategic classification. What is strategic classification? I'd like to demonstrate this through an example. Imagine you were hired to design a learning algorithm for a health insurance company. Why does it need learning? Because it needs to determine premiums for health insurances. To determine premium, it should know things about applicants for the service. So how would you start? You probably think of what would be good features to collect. And here are a collection of good features: age, current health, smoking, maybe exercise, maybe diet, etc. Now you go out to the world and collect data, then you train your model, you deploy it, and then new users come in and you start using your system. You give premiums based on the predictions of the learning algorithm. But something unexpected happens, and that unexpected something is this. Does anyone know what that is?
Strategizing the amount of steps that you take.
Yes, so this is an automatic pacing machine. It takes your iPhone and it simulates steps. Now, why would users do this? Why would anyone go to Amazon and purchase this thing? It's because premiums depend on exercise. Now, they don't depend on exercise, they depend on measurements of exercise. But if users have a way to game the system, so this is not cheating per se, right? It's not that they're misreporting. This doesn't mean how much do you exercise. This means let's tap into the log data of your iPhone and ask how many steps it perceived you as taking. Legit, right? But they find clever ways to outsmart the system because they get something out of it. They want lower premiums. And whatever reduction in premium they get, they're going to buy this machine if it's worthwhile, if the cost is lower than the gain. So strategic classification tries to model this, and there are many examples to which this applies, and actually it's a little addictive. Once you think about this, you find too many problems in which this sort of behavior appears. So think about loans. A bank offering loans would like to predict whether people are going to return or not. In the US, for example, there's an explosion of people getting more and more credit cards because the amount of credit cards you have correlates with the likelihood that you're going to return a loan. So it's favorable for people to get more credit cards, even though it doesn't change the likelihood of them returning at all. This happens in admissions, who we hire, who we accept to the university or to college. There's a story about books being correlative and people rushing out to get a lot of books before they fill out their applications. This also happened to me yesterday when my son said he was sick. Now, it turns out I have a classifier for determining whether it's okay for him to stay home or go to school. One of them is he eating enough or not? Because sometimes when you're sick, you don't want to eat. So he decided I'm fasting today. That's an indication for being sick. And just a personal story about car insurance. I'm almost sure this happened to me. I told this so many times that I'm mixing reality with maybe what I think is, but this probably happened to me. So when I was in my postdoc in the States, I needed car insurance. I called the whatever car insurance company, Geico. They have this very long list of questions. One of the questions was, do you own a washing machine? Which sounded silly to me. Why would they care? But it turns out that where I live, there was a large correlation between whether the washing machine was literally inside your house or not in the basement or shared or something to that, with the likelihood of you making a car accident. So if the cost of washing machines is lower than the premium reduction I would get, I'd go out and get a washing machine. Okay, the common thing in all these examples is that the system wants correct predictions, right? Treat this as the conditional. We want a system that's able to predict well. But in a world where users want something else, they want positive predictions. And this creates a tension between what the system wants and what user wants. Now, all of these examples are actually quite elaborate, right? Reality is messy. Strategic classification offers a very, very simple tweak to binary classification that sort of gets at the gist behind this idea. So I don't think of it as a realistic model of the world, but it's a pretty neat first step because it just takes binary classification. This is binary classification. You have continuous features, binary labels. There's some distribution. You see a sample set. You want to minimize the 0-1 loss. But in a world where users want positive predictions. And what can users do to get those positive predictions? They're allowed to change their features. Now, importantly, this happens at test time. At train time, strategic classification still assumes that the labels are unmodified. You see real features of people. Think of this as a company investing effort in collecting real data forcing people to tell them the truth in some way. But then at test time, you never see the real features, just the modified features. And these modified features depend on the classifier. Here's a way to make this concrete. For every user X, the way he modifies his features is he looks at his utility. This is what he's going to get from a positive prediction. So this can be either plus or minus 1. And reduce from that the cost from moving. So out of all possible movements, this line is making the assumptions that users are rational in the sense that they're going to maximize their utility by choosing the least costly modification that's going to improve their outcome, assuming it's in their favor, right? If they can't move, if switching to positive prediction costs more than 2 units, which is the gap between -1 and 1, they won't move at all. What does this do? What effect does this have visually? So you can imagine this radius of 2 as a ball around points. And some points, if you're classified positively, you don't move. If you're classified negatively, but you're too far, you're not going to move. If your ball intersects with the decision boundary, then you're going to move to the closest point just beyond that decision boundary. That's the model. It has a very nice interpretation as a game. That's part of the reason why this model is fun, because a lot of people in game theory are involved in this. Actually, I think you could say that this came from people in game theory. It's a very simple sequential game, one step. System chooses a classifier, chooses a new modification. Here are the payoffs. The goal is to find an equilibrium strategy for this game. And what's nice is that the solution concepts converge, right? Minimizing expected 0-1 loss is the same as finding this optimal equilibrium strategy. So this just gives another handle on how to think about these problems. Okay, but as a learning problem, why is strategic classification so neat? So in standard classification, the fundamental assumption is that train and test inputs are sampled from the same distribution. In strategic classification, this breaks. At train time, you assume unmodified samples, but at test time, you want to be good on modified samples. Now, why is this so neat? Imagine in your minds this imaginary continuum of machine learning problems, settings, where we can vary the amount of uncertainty we have about the test distribution. So at the one end, we have standard classification, where they're just the same. So you know everything about the test distribution just as well as you know about the test distribution. Maybe a slightly more complex task is this distribution shift problem. So you know they're different, but you also know something about the test distribution. For example, you see unlabeled points from there. At the other extreme, you can imagine this distributional robustness setting. So you don't know what the test distribution is, but you know it lies in some set around the train distribution. And strategic classification lies somewhere in the middle, because you can think of this as sampling X's and then modifying, but you can also think of this as sampling X's that come from a distribution that changes according to the classifier that you choose, right? This isn't general, this has structure. This has this local structure that people move rationally. But still, more generally, you can think of this as operating on the same space, but through a different distribution. And the cool thing is that the classifier itself is what determines your test distribution. So when you learn, you have to simultaneously take into account 2 things. What is the distribution you're going to induce, and what is the accuracy you're going to get on that induced distribution? And this control is only indirect because it has to go through how users behave. So it's a very neat problem. How do you approach it? So it's almost, you feel your fingers itching. Just think of it as classification with points moving, which tell you, right, going with this idea, you want an algorithm? Sure. Take your favorite classification algorithm. Just replace everywhere you see X with delta H of X and done, right? But not that easy. 2 reasons, right? These are the general reasons why things are hard. One is that this can be very difficult computationally. And the second is that statistically weird stuff can happen. So I'm not going to talk about statistically today, but it's neat. Okay, if you're interested, I can talk later. But at least for now, let's talk about the algorithm aspect. How do you train a classifier to be good on these sort of modified inputs? So if you, okay, and let's say we want to solve the RM problem. So if you look at the literature, there are basically two alternatives. One is what most people have done so far, which is design these very ad hoc algorithms. You make very, very precise and specific assumptions about the structure of the problem, what the cost function looks like, what the distribution looks like, what the feature space looks like, etc. And then you get this very neat but non-modular algorithm that doesn't apply anywhere beside the specific context. The other alternative, it's just gradient descent, right? If we could somehow propagate gradients through this objective, we could apply gradient descent, which is great because we could get end-to-end training. The problem is, of course, we need to make everything be differentiable for gradients to pass through. Why this is hard in this particular instance? It's because this delta function is an argmax, right? It's very not differentiable. But luckily, we live in a time where people have looked at how to make argmax operators differentiable. And in particular, what we did in this ICML paper is that we tried to implement this delta function as a concave optimization layer. What is a concave optimization layer? It's a layer whose output is the solution to a convex optimization problem. In this case, it's linear. But the nice thing is that it allows you to differentiate through the parameters of the optimization problem itself. This is nice. The problem is that our argmax operator, this delta function, is not concave. It has a classifier in it, right? Specifically, it looks like this. So this is just a prediction. So it's a step function over a score function. There's some cost here. Now, if you assume the cost is convex, which most cases, I mean, considering the literature, that's the case. How would you approach this? So the first step is, it's not a general step function, it's a sign applied to a scalar score function. The next step is, we do what everyone does, we replace this by a sigmoid. Easy, right? The thing is, this is not the standard sigmoid. It's a sigmoid that looks like this. I know it doesn't look like a sigmoid, but it's a sigmoid. And what's special about this sigmoid is that you can write it as the sum of a convex and a concave function. So imagine this part, and sum together, they somehow give you a sigmoid. Now, once we have this as a sum of concave and convex functions, we can apply something called the concave convex procedure, or CCP. This is an iterative process that iteratively gives you better and better concave relaxations of this non-convex function. And what's nice is that it's guaranteed to converge to local optima. So if we replace this original function with this relaxation, we get local convergence for this argmax problem. But what's nice about this specific problem is that it usually has only two local maximums, and it's very easy to guess where they are broadly. So we just initialize with two random points, smartly chosen, and at least for the small things that we've tried out, we virtually always get to solve the problem correctly. So this works very well in practice in the sense that it's a nice way to differentiate through a potentially hard problem. And we also have nice code available. I'll talk about that later. We call this Play-Doh. I'll let you guess why. And what we do in this paper is basically we show that it's very, very flexible. We can account for all kinds of, whereas most algorithms in literature just look at this one specific problem. We vary lots of things and show it works well. And we're also able to handle more elaborate models like certain RNNs, which is nice. And if this sounds interesting to you, if you want to play around with it, I have two students who implemented this in a very, very hands-on way. Just go here and enjoy. Sure. So these are 4 different data sets. Okay, this is maybe important to say at this point. When I say experiments, they're on real data, but they're simulated users. Right? To test this empirically in the world, we would need to be a bank that was willing to experiment with deploying a new classifier, right? So what we do here is we take real data and we simulate this delta function.
A question about this. So in reality, FICO scores are rarely accessible, right? So the FICO scores are not explained to people.
Yes.
People do not have perfect information. People do not know how to best respond. And in many cases, the cost function is not even perfectly understandable to people. So this best response assumptions, how do you deal with it in this expression?
Here we don't, but that's the entire next section on those sort of questions. Okay, so just back to the graph. So here we vary the scale of how much costs matter. So I think the larger this is, the harder it is to move. And what we have here is just an RNN, and what we vary is the size of the suffix. How long back? This is time series of financial data, and this is how long back you make the RNN look. Okay. Good. So that was strategic classification. I just gave you a teaser. And why did I focus on the algorithmic aspect? So it's because of this. Strategic classification is way too simple. Like Yav's question is spot on. There's so many ways to attack this model when you want to reason about what's going to happen in the real world. So here's a very partial list. This is only what I could fit. The costs are fixed, they're uniform, and they're known to everyone. Users are rational, they best respond. The system cares only about accuracy. I hope most systems don't. Users respond independently. Usually there's some sort of dependence going on, and I'll talk about that. This is a very strong assumption of modifying X does not change Y at all. You can imagine that in most settings, some changes user makes are also going to affect the outcome itself, right? If for car insurance, if one of the features is going to driving school, driver as ed, thank you. That's potentially supposed to also improve your driving. Whether it does that or not is arguable, but this is completely hidden under the rug. Playing order is fixed. Why does the system get to play first? Why is this only one round of playing? Why is it not an iterative play or something that happens over time? Why is it assumed that the system has access to unmodified inputs at all to begin with? Why is the classifier made public? For users to best respond, they need to know the classifier. Do they always know the classifier? Even if they were rational and could infer this, compute this argmax exactly. Lots of ways to attack this, which is great because it gives us opportunity. And when I see this list and when I have an optimization algorithm that I can just run on data, my fingers start to itch and I want to try things out. And this is what's going on in our lab. We have like 5 different students, each attacking a different part of this and trying to think of what's interesting. And what's neat is that when you make these slight changes, when you relax assumptions, or when you place this in a different context, then very nice learning problems come up. You make a very mild change to the problem, but you get different phenomena and different kinds of questions you can ask. So I'd like to give you a very quick tour of, I think, maybe 6 things. Let's see if we have time. We have until 11:30, right? I think, okay, should be fine. Okay, let me know if this is too fast or too slow. Okay, let's start with this. System cares only about accuracy. Who would want to join a service if the service only cared about its own accuracy? Likely no one, right? We use systems because they're supposed to also be in our favor in some sense. And when you look at these large systems, they don't determine things only for their accuracy. They have other considerations in mind. How would you make this sort of learning framework be aware of other considerations? So let's first talk about the problem. So here's standard classification. Here's the negative class, here's the positive class. You can put a separator here, you get perfect separation. What happens when people can strategize? Then all of this part of the distribution can move here, right? These are people who it's worthwhile for them to invest effort in modification so that they get positive predictions. So strategic classification says, okay, let's take that into account. The way to take that into account in this example is just to move the classifier. Right? It raises the bar. It makes it harder to be classified as positive. So everyone in the negative class is now too far away to change. But what happened unintentionally maybe is that all these positive guys now have to invest effort just to get the label that they deserve. This is a bad property of the system. Right? People who are supposed to get low premium don't need to go out of their way to get reasonable premiums. Okay, how can the system account for this? It can happen in this example because this may look 2-dimensional, but it's actually 1-dimensional. So the system has very little degrees of control, but you can imagine that in higher dimensional problems, the system might have some flexibility. So think of this as regularization, saying of all possible models of high accuracy, let's choose the one that's the least bad for users, or we promote social good at as little cost to accuracy as possible, right? This is in a sense the essence of regularization. It's not helping generalization here, it's helping some other objective. So we tried this out. The positive users having to move is a measure called social burden. We're able to encode it as a function. And when we plug it into objective and look at this empirically in our semi-synthetic experiments, what we get is these very nice trade-off curves. So this is showing that adding it more and more regularization, you pay virtually no cost in accuracy, but you get about half of the increase of reduction in social burden you could get by completely discarding accuracy. So this is a very neat property of the problem, and I hope it holds in reality. And the only thing that's going on here is that we regularize in a smart way. And we did this for other two sort of social good measures. One is expected utility, how much users get, and the other is recourse, which is what percentage of the deserving population is able to modify their features to get positive predictions. Okay, questions about this? Great. Second thing. So this is a point Yav brought up. Strategic classification assumes that users have perfect knowledge of the classifier. How can they have perfect knowledge of the classifier? You can think of this as assuming that the system makes the classifier public. Now, sometimes this makes sense. And there's a lot of pressure on companies to make their models public and understandable and explainable, etc. But for credit companies, this isn't exactly the case. So Schufa is the credit scoring company in Germany, right? They're in charge of indexing every single person with a number indicating how worthy they are of receiving credit. It keeps its algorithm hidden. You know your score, but you have no idea how the algorithm operates. But OpenSchufa is a public initiative of people gathering lots of data, asking people about their credit scores, about their data, about what happened to them, and trying to reverse engineer the algorithm. So what these guys are doing, and I think they're doing a pretty good job of it, is they're giving people access to the model itself. They're allowing them query access to an estimated model, also based on data. So it's like a small Cold War. Strategic classification operates in this transparent policy, right? It assumes that the system releases the classifier and then users can use this classifier to modify their inputs. The alternative is to be opaque, which means I'm going to learn a classifier, I'm going to keep it to myself, but I'm also going to assume that people operate based on that. That's a catch-22, right? Because how are people going to move according to a classifier if they don't know the classifier? So I could not take this into account, just learn a classifier without assuming any movement, but then people are going to move, so that's necessarily not optimal. So the way we get around this is that we imagine this optimistic firm, which we think makes sense. It's a firm that says, we're going to keep the model hidden, but we're also going to assume that information somehow leaks out. So people are going to know, they're going to get examples of how our model works by seeing classified inputs. So the system sees X's and Y's, users see a small number of X's and H of X's, how the system classifies. And they're going to build an estimate of that function. This is supposed to mimic what OpenSchufa does. And then users are going to operate based on this. And we ask the question.
OpenSchufa was trying to mimic real Schufa?
Yeah. Reverse engineer it. So a system that chooses an opaque policy is going to be optimistic in that it's never going to know this estimated H. It's going to assume that users use something that is close to H. So working with H is probably okay. Right? There is going to be error in this estimation, but the naive assumption here is that this error is just going to be maybe additive or go away somehow. But what we show is that it doesn't go away. It can actually explode. Right? You can construct certain instances where the gap between wanting to know what users do exactly and imagining you do can go very bad very, very quickly. And sure.
So in those settings, so the question is about the assumptions. So you can think of a loan approval setting where people do not know exactly the model, but they know what features correlate positively with the competition. So you know that having a higher income in every reasonable model is a good thing for you if you want to do it. Or if some other features, you know whether they are negative or positive
Correlated
Yeah, correlated.
or causal?
Correlated with a good prediction. So
Okay.
point is, even if people do not have any information about the model, it's reasonable to assume sometimes that they know what features are good to manipulate in what directions.
Yes.
So how does that relate to this price of?
Okay, that's a good question. Can we rephrase what you're saying as modeling users as Bayesian? They have some prior on what features, on how features affect the classifier, and then they work on that. Okay, so if you think of this as an empirical based users, I think you get the same results. But if you hard code some prior, analytically, I don't know how to get the results, but I would imagine they hold. But no, right,
So
no
the
guarantees.
question is, so do you think that when people have no formal information, they do not manipulate or they do not act?
That's a good question. We don't go there. We assume people know something, and the something is based on data. If you want to replace that with a prior assumption, I think it's legit in the same way. Okay, but the structure of the problem is itself holds, right? They're never going to get H exactly. There are going to be some errors in how they move relative to how they should have moved with H, and that's easy to blow up. So we also tested this empirically on loans data. And you see that the price of opacity, this pop thing, is really, really large, even as you increase the number of samples exponentially, right? This is an insane number of samples. No one knows 100,000 people. And still, the estimation is very, very good, but tiny errors in estimation completely blow up because of this strategic movement. And that's what I was trying to say. You change something very mild about the problem and you get this very interesting behavior. Okay, and what we also did is that we told these nice stories. We took the specific loans data we worked with, had an underlying social network. This is a peer-to-peer loan system. So users are connected to each other. And we sort of looked at this as a proxy for where people get their information. So we assumed that this user observed the features of a subset of his neighbors. And then you can look at how does your position in the network and the identity of your neighbors affect who you are and what you can get for the system, for good or for bad. So here's a user who's accurate but moved unnecessarily just because his information was inaccurate. Here's someone who moved in the wrong direction. If he stayed put, he would have been classified positively. But having lots of negative neighbors somehow changed this. So this is not accurate because it's a 2D reduction. This is, I think, 15-dimensional, something like that. So it's not an exact picture, but it tells the story. Okay, question about public classifiers? Okay, next assumptions. Users respond independently. This delta function applies independently to each X. Now, this is strange because when you look at how game theory people look at this problem, they don't think of individual users. They think of a single users, capital U, entity who plays everyone at the same time and he cares about the expectation. So somehow it doesn't matter. But there are real people involved. And when you start getting dependencies, then that breaks completely. There's no single entity. The way people act affects each other. So if you go back to these examples, I portrayed them as classification. And for a long time, they've been thought of, sure, these are classification problems. They're actually ranking problems. Why are they ranking? So for example, think of loans. The bank doesn't have an infinite amount of money. It can't classify everyone positively. You can't hire everyone. You can't accept everyone. There's competition. Ranking is one way to think about it, right? If the decision rule is first rank and then cut at some K or based on some budget or something like that. So these are all problems where you actually have scarcity. Scarcity adds dependencies between how users move. You can no longer think of people as just trying to affect their prediction because their prediction now depends on others, right? So this becomes a much more involved problem where users are supposed to optimize their rank based on how they believe other users are going to optimize their own rank, knowing these users are also going to optimize this rank. Now, this is confusing even to me. I don't get this game theory stuff completely yet. But the nice thing about this problem, we don't show this yet, but we believe it holds. This has a property in which something called best response dynamics. Thank you. This is If people move, assuming no one else moves, and you repeatedly apply this process, it's going to converge, and it's going to converge to the equilibrium you would have got had everyone taken into account what everyone else is doing at the same time simultaneously. So it has this very nice property, and what we're hoping is that if we can design this architecture or model that simulates this iterative process, then we're able to learn in a way that I think about, okay, never mind. Okay, so that's users respond independently or not, number one. Here's number two, that's also related to the fact that costs are fixed, uniform, and known. This to me is the most annoying assumption. Where does that cost function come from? Why should there even be a fixed cost function? Why should the system know it? Why should users know it? Who determines this thing? Here's an alternative suggestion. It's modifying the problem, but I think it's getting at something that's underlying this annoying property. Here's a simple example. Two users, I and J. Two features, the numbers of bananas you own and the number of apples you own. So both of them have one apple. This guy has one banana. This guy has 3 bananas, maybe. Okay. This would have been a silly strategic classification problem, but the twist is now that there's a shop selling apples and bananas. And in this particular example, there's 1 apple and 1 banana. Now, users can't just conjure new bananas. They need to buy bananas. That's what happens in the world when you need stuff. You buy it. So they go to the shop. The thing is, they have budget. So imagine this BI and BJ as the dollar budget each user has. The fact that users are interested in positive predictions creates demand. The demand is to be classified positively. The classifier is creating demand. The shop is creating supply. And when you have supply and demand, what you get? A market with prices. And what's going to determine prices is the relation between supply and demand. And that's going to be a function of who the users are, what their budget is, and what the system decides the classifier is going to be. So here are 2 examples of classifiers that induce completely different behavior. One classifier says, look only at bananas. Bananas are important. Now, assume J's budget is smaller, but because he's closer here and because there's only 1 banana available, he's going to get it. Prices are going to be set in a way that only this guy is going to get it. So he's going to be classified positively and I is going to be classified negatively. But if the system chooses this classifier, then because this guy has a larger budget, he's willing to pay more. Prices are going to go up and he's going to be able to buy the apple because he's not going to have sufficient budgets to buy an apple. And now he's going to be classified positively. So now the system is not only deciding who gets positive and who gets negative classifications, they're choosing, is it important to have bananas or is it important to be rich? Which I think has significant implications on how we think about classifiers in general. Now, bananas and apples are admittedly silly, but just swap them with GPA scores and SAT scores. These are ממוצע בגרות ופסיכומטרי. There's a huge market for SAT prep schools. Probably most of us have paid tons of money just to increase our SAT scores. Not because it helps us in life somehow, just because the academic system decided that that's the classifier it's going to use. It's some weighted combination of this and that. Had they chosen differently, prices would likely be different, right? If tomorrow they decide to give very low weight to SAT scores, courses are going to be much cheaper. Places are going to shut down. Less people are going to take the courses, etc. So we believe that there are many real significant problems that have this structure, that classifiers induce markets. And I think it's neat to think about how to learn in a way that takes that into account. Okay, user respond independently, number 3. In many cases, users are connected through a social network. So I brought up that loans network, but think more broadly. All of us are somehow connected to everyone. That's become very popular. And there's one branch of machine learning which designs predictive algorithms that use these graphs in addition to features to make better predictions. They're called graph neural networks, even though they were way before anyone talked about neural networks. If anyone's familiar, label propagation. I gave my master's talk on label propagation. Not in this room, but okay. So now imagine a system that says, hey, we have features. We also have a graph. Let's use both. Let's use one of these cool things. These things work well when Okay, these things work well when the graph gives you additional information to the features, like complementary information. And what the smart engine behind this is how to balance what you get from features versus what you get from the graph. The way most of these things work is by embedding. So they take a node with features xi, and they embed it in some latent space. Sometimes it's the same ambient space in a way that depends on its neighbors. And usually it's linear, right? It's some weighted combination of the node's features and its neighbor's features, where these weights are determined by the graph. And usually you normalize, so you can think of it as some convex combination of yourself and your neighbors. Just think of this as points moving. I have an illustration, I think. Okay, and then once you get these embeddings, you just apply a linear classifier on top. Yes, so pictorially, what does this mean? Here's xi. Here are his neighbors. Now, this is the embedding. And imagine what this line is how much you rely on the graph. Imagine there's this single parameter. This is not thinking about the graph at all. This is discarding feature information and just looking at the average of the neighbors. And the system has control over how much it wants to use the graph. And you can think of non-strategic settings as, let's find, this is simplifying, right? But let's find the optimal amount of graph we need to put in to get the best performance possible. The problem is that once users respond, things become very difficult very fast. Why? Because now what's actually moving is their embedding. But how much they can move depends on how much you use the graph, right? If there's no graph, then the ball is pretty large, but it's far away. If you use only the graph, there's no use in moving for yourself, right? Unless you're benevolent and care about others, why move at all? You have no effect on your embedding. And anything in the middle is you are closer, but the ball is smaller. So there's a trade-off here. And what's neat is that the system utilizes the graph in a different way than how users use the graph because of this one-directional things, right? They want positive prediction. System wants correct predictions. And if you're not smart about this, then you can use the graph in a way that actually hurts you just because people are moving. More than if you didn't use the graph, and still people would be strategic. And the interesting learning question is, how do you use the graph in the right way? How do you preserve robustness to users modifying their features despite using the graph? Questions? Okay, next. Never mind. Okay, this is the last one, I think. Yes, this is the last one. Strategic classification assumes the system first chooses a classifier and then users modify their inputs. This tells a story of evil users that game the system. The system just wants accuracy, but here come users and they misreport, they change things, bad users. In reality, I'd like to argue that it's usually the other way around, where systems are powerful computationally, they have tons of data, they control information. It's fairly easy for them to game us into doing things. So how do we model this? Here's an example. So just recall the last time, this may be a while ago, but the last time you tried to book a hotel and you go online, how are hotels described to users? Do you get to experience being in a hotel by looking at a web page? No, you get some filter, through some filter, this information is passed. In particular, there may be lots of images, and what you see is a select 5, 6, 7. And this is supposed to help you determine the value of the hotel to you, whether it's worth to go there or not. But who chooses this subset? Who chooses which of the 50, 100, 1,000 images goes into this thumbnail? Is it some benevolent thing, like we want to put the pictures that are best for you? Is it some naive statistical criterion, or is this the system optimizing something which may or may not be in our favor, but it's usually blind to what we care about? So how do we model this? It turns out that you can think of this as strategic classification just flipped. So users have value functions, but when they get to choose, this is a choice function, they don't see the true item. They see a representation of the item. This representation is controlled by the system. And what we assume here is that the way the system chooses the representation depends on how people choose. This is a stylized model where we assume people just give the choice function, but you can imagine this is coming from data. The system observed lots of past user behavior. It can infer. This is the goal in personalized services, right? You want to infer how people choose and give them recommendations accordingly. The system, at the same time, just wants to optimize people choosing stuff. But there's a cost to this. And here, the cost is different because, okay, for reasons I don't want to go into, we think of this in a discrete setting. Like images, you need to choose a subset. So what we allow the system to do is to choose a strict subset, right? It can't conjure up new images. It has to be truthful in that sense, but it has a budget. Think of this as the cognitive capacity or the platform capacity. You can't show 100 images. You're only allowed, there's space for 10. That's what you have to work with. Now, what we ask here is how bad is it for users to not strategize, to sort of be naive, say, I'm going to choose according to my preferences. I see something, I imagine this is reflective of the true value, and I choose based on this. And it turns out that the gap can be arbitrarily large. It's not very interesting because it just shows that there's some distribution, which it doesn't work well. But then we have ways of showing that this likely happens more often than not. And then the question is, who is gaming who now? Okay, so that was a quick and thorough tour of some of the projects. Some of these are, I didn't say this, some of these are the published work, some of these are midway, some of these are just half-baked ideas, but just to give you a broad scope of what is possible in this space of strategic classification. Okay, but what lies beyond strategic classification? So I started out by saying we have this vision, we maybe want to get there someday. We start here, and strategic classification, if you agree with me, is at least an interesting first step along the way. And here are a bunch of other things, ways we can extend strategic classification. But where's this going? Is this going to reach this grail? Probably not. And pictorially, I want to show this by saying that it's probably not a linear staircase. It probably looks more like this. And here's an example. Okay. I talked about supervised learning. I think I said machine learning throughout, but what I actually meant is supervised learning, right? There are other ways of learning. But in the supervised learning setting, machines make predictions and humans take actions. They do things. Oops, sorry. And doing things is completely outside the scope of supervised learning. Supervised learning is all about correlations and predictions. Once stuff gets done, it's very hard to handle. But there are other ways to handle actions. So game theory is a very good place to go if you believe people strategize. And game theory gives you tools to talk about equilibrium. But what happens on the way to equilibrium? For that, we have system dynamics. System dynamics is a great tool for thinking about what happens until you get to equilibrium, whether you get to equilibrium, etc. But system dynamics takes a very passive stance. You don't do anything. But we have online learning. Why not think of this as a bandits problem? We get to pull stuff and things happen along the way, and we should pull them smartly. But bandits assume that our actions don't change anything fundamental in the world. But we know that these systems make changes, right? Think of recommendation systems. Every time the system recommends something, it's making a change. By deciding what information to expose to us, it architects the choice set we have. That's going to have an effect on the future. So this is actually a reinforcement learning problem. Maybe we should model it as reinforcement learning. But reinforcement learning does stuff and changes the world without knowing the effects of these actions, except the reward of the agents. And because we're talking about real social systems, people are going to start asking, what happens when you take these actions? Right? You want to reason causally about what we're doing. So what is the correct answer? I'm not going to give an answer to what is the correct answer, but I'm going to give one perspective. One option is to have very relaxed, quiet, understanding conversations about what approach should be taken. That's great, but while we make these discussions, what's going to happen in the world is that 18-year-old nerds are going to take online courses and use open source software to solve real-world problems like they would these silly competitions. That's going to happen. In my mind, that's inevitable. So the way we think about how to approach these very difficult tasks in which machines learn and people do things is stay in supervised learning land. Okay, supervised learning, you can think of this very shiny thing that everyone wants to use, but it's also very wrong, right? It's not the right tool for the problem. And this is inevitable. But there are other tools that you can use, right? Game theory, dynamics, bandits, reinforcement learning, etc. And what we try to do is sort of compress these very strong engines into something that looks like supervised learning from the outside, but has this internal engine on the inside. I think of strategic classification as a very simple preliminary step in this. You take the fundamental supervised learning problem of binary classification, but plug in some game theoretic aspect. But this is completely hidden from, this is abstracted away from the designer of the system. He doesn't have to understand game theory or do anything. This may be a little extreme, but I imagine this as being, take scikit-learn and add this little flag, humans do things, and take into the account. This is very simplistic. It's probably not the right thing to do, but maybe it's one step toward the right thing to do. So with that, I'd like to end. This is the message, machines and humans. It's a mess, but it's also cool. Thank you.
So here, I think this, depicting this as a two-player game where you have this arms race between this algorithm designer and users is maybe overlooking the fact that in some cases the algorithm designer is also interested in more positive predictions, more positive, really positively labeled people. So for example, in loans, you could think of the bank not just wanting to have perfect accuracy, but have more qualified candidates.
Yes.
And making more money off of them.
But this works only if Y can change.
Exactly. So when thinking about these classifiers, and you say gaming, do you also refer to the ability to improve? Or this is just taking the view of
Okay, so strategic classification takes the gaming approach, which it explicitly assumes that changes to X do not change Y, which is why they allow themselves to call it gaming. But even that doesn't necessarily mean it's gaming. There are two projects I didn't bring up that relate both to this question. One is a project where we do allow Y to change. And while the system wants accuracy, it also wants users to not do stupid things. Right? The rationale behind this project is, okay, imagine this heart risk calculator. If anyone was curious about their heart risk, maybe you went online, it asks you to fill out these things, age, weight, etc. And the modern tools don't only give you a health risk, they also tell you how each of the factors affect the score. This is begging for people to confuse correlation with causation. This is also confusing to doctors, and I've talked to doctors about this. If there's a large coefficient on sleep, you'd be tricked to thinking that taking a nap is going to reduce your heart attack risk. And this is, you can't work around this. This is something fundamental to our nature. We are going to confuse correlation with causation. So that project is about learning models, which taking into account the fact that people are going to move in a way that the model predicts is going to improve, make sure that they don't do silly things, which initially translate to make sure people move only to regions of high density. Don't push people to places where you're uncertain about what's going to happen. That's one way to think about it. The other project is that you said about systems not caring only about accuracy. I think users don't always care about only positive predictions. In many cases, users and the systems want accurate predictions. Recommendation is all about everyone wanting the system to know what you want. And then the question is, the incentives are aligned here. But if you don't learn in a way that takes into account, you're missing out on something. So this project is about how do you learn in a way that utilizes the fact that people are willing to invest effort to improve everyone's outcome. And the interesting question there is, how do you balance this? How do you not get people to feel like they're flying? I don't want to move just to improve everyone else. It becomes a sort of free riding problem. So these are definitely questions which I think are worth asking. They're certainly behind the scope of the narrow definition of strategic classification. But the one of the points I wanted to make here, it's a first step. Now we can think about other stuff.
So if you go back to the definition of strategic classification, isn't it exactly the same as what other people call adversarial learning?
Oh, thank you. I was waiting for this question. Okay, it's a complex answer. Okay. What you asked is whether strategic classification is like adversarial learning. Superficially, they look similar, and they have similarities. So adversarial learning, once I primed you to thinking about strategic classification, it may sound like adversarial learning is just system wants accuracy, users want negative accuracy. Right? They want the system to fail. This makes it a zero-sum game. Whatever the system gains, users as a collective lose. Whatever users gain, the system loses. In that sense, it's way more restricted. There's only one dimension you can play in. When the system wants accuracy, but users want positive predictions or other things, you get this structure, which has a lot of variations once you add more dimensions to the problem. So there's much more flexibility. But there are also other nuances. If you look at the literature, this doesn't have to be the problem itself, but the literature of adversarial learning as it is now, you see the adversary attacking the loss, not the classification. This essentially makes it a regression problem, which is structurally very different from the classification problem. The argmax you see here, the step functions, all the non-continuities don't exist there. But it also has another effect. The fact that users operate in the other way and that it's a regression problem means that users are always going to move to the largest extent they can. So it's not a question of how do you maximize inside the ball. You know you're always going to get to the circumference of the ball. It makes the problem much easier. On the other hand, usually adversarial problems are considered in these very complex, deep neural networks where it's very hard to compute the optimal adversarial action. So what you do is maybe you take gradients through X or something like that. The algorithmic aspect is different. Here, we intentionally make the assumption that the model is simple. If the model is not simple, people will not know how to act. So this is, yeah. Okay, so there are relations, but it's different. And it becomes a completely different problem once you step outside of the original narrow strategic classification problem and think about these more complex market settings or inverse setting. That's completely off. Okay, but thank you for asking.
Looking forward. Thank you for this great talk, and see you all next week.